Hello, everybody. It is my great pleasure to introduce Dr. Alessandra Caraceni, an accomplished Italian mathematician whose work lies at the intersection of probability theory and stochastic processes. Dr. Caraceni received her PhD in 2015 from the Scuola Normale Superiore di Pisa, where she wrote his dissertation uh, titled The Geometry of Large Outer Planar and Half Planar Maps and the Supervisions of Nicolas Curien and Franco Flandoli. Following her doctorate, she served as a postdoctoral researcher at the University of Bath from September 2016 to March 2019. Her research is centered on the geometry and the growth of random planar maps, and she has made significant contributions toward our understanding of uniform planar maps through her publications. Beyond her research and diverse, Dr. Caraceni is deeply committed to mathematical education and outreach. In 2015, she led the Italian team at the European Girls Mathematical Olympiad. Since then, she has continued to support this team, serving as a coordinator and playing a role in the selection of problems. We are privileged to have Dr. Caraceni with us today, and we look forward to benefiting from her insights and expertise. Thank you again, Dr. Caraceni, for your acceptation, and please, you can start.
Well, thank you so much for the invitation to speak at this seminar. Introduction. So today I'm going to talk about some joint work with Nicolas Curien and Robin Stephenson. And I'm going to mainly focus on random trees and let's say process for growing trees uniformly at random. So my idea today would be to give you first a pretty gentle general introduction to my specific notation and to the background I will need to introduce the problem I'd like to explain to you. So for now, just bear with me as I introduce all of the elements that we'll be needing throughout this talk. And first of all, I would like to clarify what I will mean throughout the talk by a binary tree. So we'll be talking about growing binary trees uniformly at random. By a binary tree, I will mean a plane tree. So a tree in the graph theoretic sense, but endowed with a root vertex that also naturally induces a genealogical structure on the tree. So each vertex, other than the root vertex, will have a parent and potentially some children vertices. And what I mean by when I say a plane tree is that, in fact, it is also embedded in the plane. So also, children of a certain vertex are considered to be ordered, let's say in clockwise order around this vertex. And so, all right, I'll be talking for at least 80% of this talk only about binary plane trees, by which I will mean that the vertices have either degree 1, in which case I call them leaves, or degree 3, in which case I call them internal vertices of the tree. So each internal vertex has for sure a parent and a left child and a right child. Now, in this definition, I've written something slightly unclear in the sense that the root is a distinguished vertex of degree 1, which I actually prefer not to count among the leaves. And so I will say a binary tree has size n if it has exactly n internal vertices. And if a binary tree has size n, then I will consider it to have n plus 1 leaves, plus the root vertex, which doesn't count for me. Now, some people would call this set Tn, curly Tn, as I've called it, for now, rather than the set of binary trees of size n, the set of Catalan trees of size n, unsurprisingly, because it's not difficult to enumerate our set Tn and find that the number of possible binary trees of size n in this sense is just the nth Catalan number. And indeed, this just comes from the fact that these trees have a very evident recursive structure. So you have your root vertex. Your root vertex has one child that is, if the size is more than 0, an internal vertex. And onto this child are grafted a left subtree and a right subtree. And those two trees can be seen as binary trees themselves. And so the cardinality of Tn just satisfies the recursion for the Catalan numbers. All right. Yes, and this is what I meant to say. So a very first question that we might want to investigate, and a classical one, is, all right, now suppose small tn is a random variable taking a uniform value within my set of all possible binary trees of size n. So I'm picking a binary tree of size n uniformly at random. My question is, well, what does this random object typically look like? Usually we ask these questions in terms of, well, what are the typical properties of this object for n large? There are, of course, several ways to even just approach this question. One possible classical way is to look at what these trees look like if I sample larger and larger ones. So this is an example of a sample of, let's say, T10, so 10 internal vertices. This is T50. I might want to look at what they look like globally, in a sense. So by looking at the whole tree at the same time, the large-scale features of this tree. And these are larger and larger trees. If we want to make sense of this question in terms potentially even of some limiting random object when your size n tends to infinity, one way of doing this is just to consider our random tree Tn as a pointed metric space. So you could just think of this as a metric space by taking the set of vertices of Tn equipped with the graph distance on this set of vertices. Just the distance in the graph theoretic sense, the shortest, the length of the shortest path from one vertex to another. Now, this way, Tn can be interpreted, or let's say induce, well, as a finite random metric space. To be fair, well, from the metric space, you can, of course, recover the whole graph theoretic structure of your tree because you know what vertices are neighbors to each other. And you're considering pointed metric spaces usually, so with endowed with one distinguished vertex, which will have been your original root. As a matter of fact, with this sort of notation and setting, by passing to the metric space setting, we're actually forgetting the embedding into the plane, in the sense that from, well, the fact that we were considering plane trees in the beginning will affect the distribution of our random metric space. But if you give me a sample of the random metric space, I'm not able to tell which children were left children and which were right children. But this, well, technical detail is will not be relevant in what follows. In any case, so the aim is to produce a limiting object, some sort of limit in law for these random metric spaces. In order to do that, we would need a way to compare random or even deterministic compact metric spaces to each other. And one natural way to do this is via the so-called Gromov-Hausdorff distance, which is not difficult to build from the Hausdorff distance. But I won't get into the technical details here. If you're not familiar with this subject, you can just, well, sort of look at these larger and larger samples of plane trees that I'm trying to build a limit of. Something, though, that should sound quite natural is that in order to obtain convergence of this sequence, to actually make these trees comparable to each other in the Gromov-Hausdorff distance, I will need some sort of a scaling factor, because these trees, in terms of the graph distance, just become larger and larger. I'll need to rescale these metric spaces by essentially the typical, let's say, diameter of the metric space when it has size n. So in fact, the typical height of a uniform binary tree of size n. And it is a classical result that the typical height of a uniform binary tree of size n is of order square root n. And so the convergence result that I'm trying to express, here you see an even larger tree that is now drawn on the plane in a way that's a little bit different and just done by letting Mathematica do its thing. But also it looks a little bit more like what it's supposed to look like, in the sense that the previous trees had edges of kind of different lengths, and the edges of this tree are trying to be more or less of similar lengths to each other.
Please, can I ask you a question?
Yeah, of course.
What is the definition of DGR? The
So
distance.
yes, DGR is just the graph distance. So at a discrete level, you have your tree Tn. V of Tn is the set of its vertices, and the distance DGR, if you take two vertices of the tree, is just the number of edges in the shortest
Okay.
path
And Rn,
from first to second vertex.
Rn what
And
represents
Rn is just the root vertex.
Okay, okay. And
So the
okay. And for our public, can you please give the definition of the height of the binary trees?
all
What?
right. So the
Okay.
height of the binary tree is just the, well, the maximal graph distance of a vertex from the root vertex.
Okay.
Or if you like, well, the genealogical structure of your binary tree will have a number of generations. The root vertex is the 0th generation. The children of the root are in the 1st generation, etc. And the height of the binary tree will be, well, the total number of generations, let's say, not counting the generation of the root vertex.
Okay, and the diameter, what is the diameter of the
So the diameter in terms
diameter?
of just in the metric space language, we just mean the maximal possible distance between two vertices or 2 points in
Okay,
the metric space.
so it is
And
different. Sorry, it is different from the height. It
I
is
was
not
about to say, yeah,
okay.
it's different from the height in the sense that, well, it's yes, it is. But in terms of its growth, it's really the same as the height. And essentially the diameter will be, well,
Okay,
kind of you expect it to be about
okay. Thank
twice
you.
the height,
Thank you.
perhaps. So I will sometimes use diameter and height interchangeably. In fact, it's more convenient to just work with height in the case of trees, and in fact, in the language of metric spaces, in a sense, I'm working rather than with the diameter, which lets both endpoints of the geodesic path change. I'm working with a radius, so I'm fixing one endpoint of my geodesic path and looking at how far from that point, which is my root vertex Rn, is the furthest point in the tree. And indeed, that will be a vertex at maximal height. So, okay, in the drawings that I showed you so far, what did we have? We had random, well, you couldn't quite tell they were random, but they were random samples of plane trees of size n, rescaled with the height. So in fact, they all fit basically within the same size square in my slide. And that's the sort of random object for which I can actually define a limit as n goes to infinity. So I won't go more into detail about this, but you can take this sequence of random, compact metric spaces, or if you want to be even more precise, of isometry classes of compact metric spaces. Take the limit in distribution for this Gromov-Hausdorff metric and obtain an object that was introduced by David Aldous in the 80s and which is called the Brownian continuum random tree, and which is a random compact metric space itself, pointed, if you like, so we can keep track of where the root is supposed to be. And which is now actually a continuum metric space and no longer discrete as its finite discrete approximations were, and is a very, very fractal object. It has Hausdorff dimension 2, actually, but it is still a tree in an appropriate sense. No longer in a very easy to explain finite sense, but as what is called a random real tree. And what you see on this slide is just, well, of course, an approximation of the Brownian CRT. So this is a finite tree, but you should think of this Brownian CRT as an infinitely intricate metric space object that is everywhere tree-like. Now, I will need a couple more ideas about this infinite limit of random plane trees. One thing that I should probably mention here, and that is especially nice about the Brownian CRT, is that it is a universal kind of limiting object. So, in fact, I'm writing this theorem here by saying that it is the scaling limit of uniform random binary trees for the size being sent to infinity, but it also is the scaling limit for a wide range of different possible models for random plane trees, not just necessarily binary trees. For example, if you were to attempt the same construction with, say, k-ary trees, since I will mention them perhaps later, and by k-ary trees I mean that internal vertices will just have degree k+1 instead of degree 3, as I described before. What could sound surprising if you're not familiar with this setting is that, in fact, the scaling limit is indeed the same, up to potentially just constant factors in front of the distance. It is still the Brownian CRT. And so in particular, even if you take, say, the scaling limit of uniform random k-ary trees, you will still obtain something that only has binary branching points in this continuum limit, which is quite interesting. And there's a whole field of study. You can, for one thing, try to better understand this universality ideas. Models for random trees are not the only geometric objects that actually do converge to the Brownian CRT in the scaling limit, but even certain random maps with one or a few macroscopic faces might converge to the same object. And you can study plenty of statistics on the CRT itself. And something that we might mention further along in the talk is, for example, something you can do is compute the precise density of the distribution of the height of a uniform random leaf in the CRT. Now, since I just mentioned the idea of picking a uniform random leaf of the CRT, let's add a little element of technicality to what we've done so far, because we might need this later. Something you could do, some further structure you could have tag along onto your finite random trees at first, and then have a limit emerge in the setting of the CRT, is you could be considering the metric space given by the finite random tree Tn endowed with a measure, μn, let's say the uniform measure on the set of the vertices of Tn. And what you might want to do is to keep track of this measure and see whether there's a way to obtain a scaling limit that also has a measure on it, which would naturally be what we would call the uniform measure on this limiting CRT. And it turns out that up to, setting everything up correctly, you can still do this in a way that's not much more complicated than the Gromov-Hausdorff convergence that we mentioned before. What you need is a type of convergence that we might call the Gromov-Hausdorff-Prokhorov convergence that also keeps track of this measure, and you end up with, let's say, a limit mu for this sequences of measures, mu n being a measure on the vertex set of Tn. Mu would be the uniform measure on the CRT. Now, just to give you a bit of an idea how the CRT works, it shouldn't be too surprising if I tell you that actually this measure is concentrated on the leaves of the CRT. Now, you might ask, well, this CRT is not a finite tree, so what does it mean for a vertex to be a leaf of the CRT? Well, we could just say that the leaves of this limiting metric space are the points for which, if you take away that point, only one connected component of the CRT is left. You're not decomposing your tree into two or more separate connected components. And you could call branching points of this infinite continuum tree the points for which, if you take them out, you see strictly more than two connected components. And in fact, you will always see only three connected components, is what I was mentioning before. Now, all other points are those that you would think of as being points within a branch of the tree. Those that, if you take them out, leave two connected components of the tree. And this uniform measure on the CRT actually only charges the leaves of the CRT. Those have probability 1. It's what's quite obvious is that the branch points would have probability 0, and in fact there's a countable number of branch points, so that's quite natural. But the other points, the ones that are not branch points or leaves, also have measure 0 according to this measure. And I think this is all the information I want to give you about the CRT and about the continuum part of the story. We will get back to some results that sort of complement this classical background at the very end. But just in case your preference is for more discrete ideas, we will go back now to finite and discrete trees for a while and introduce the main question that I wanted to talk about in this talk. That is, I've just described this random, uniform random binary tree of size n, Tn. And of course, I could also sample Tn plus 1, the uniform random binary tree of size n plus 1. Normally, I've just made these two samples in two different probabilistic worlds. They don't talk to each other. My question is, let's say, could I actually couple these two random variables, so sample Tn and Tn plus 1 at the same time, in such a way that Tn is a subtree of Tn plus 1? So, in other words, what am I wishing to do? I'm saying, well, I would like to sample my uniform tree, Tn, and then I would like a way to choose a leaf of Tn, conditionally, potentially, on what Tn actually looks like. Choose a leaf according to some random way, in such a way that if I grow two children from that leaf, the random tree I obtain has the same distribution as Tn plus 1. So in a way, you could think of this as just having the sun that will give some light to each leaf of my tree Tn. And then I could sample a leaf of Tn proportionally to the amount of light it gets from the sun and see what happens if I just grow a cherry, two children, turn that leaf into an internal vertex, and give it two leaf children. And the question is, can I have a light distribution on the leaves of this tree such that if I grow my tree according to this light distribution, then I obtain a binary tree that's uniform among all the binary trees of size n plus 1. And now at this point, some of you might be a little bit confused in the sense that the first idea one might think about is, well, what's the issue? I could just distribute the light uniformly onto the leaves, just pick a uniform random leaf and grow there. Wouldn't that just give me a uniform random binary tree of size n plus 1? And the answer to that is definitely no. One thing that is worth maybe reflecting on is, well, I tried to sell you that the total height of a uniform binary tree is of order square root n. But if I build a tree in this way, by at each step picking a uniform random leaf, what sort of height would you expect to see for the result after n steps? Well, one rough way to get an idea is, well, the height will increase by at most 1 at each step. And in fact, it will increase by 1 only if I pick a leaf that was in the top generation at the step before. So just as a heuristic, I would sort of expect the average height to be of order, well, maybe 1 plus 1/2 for the probability that I pick a specific leaf at the next step, plus 1/3, plus 1/4, and so a harmonic sum that would give me a total average height of order log n. This is not quite precise because there might be more than one leaf achieving the top height, but the intuition is correct. The average height of a tree that I build in this way is of order log n times a constant. And indeed, this model of a random tree that I obtain by just adding a pair of leaves at every step, many people would call probably random recursive trees. And they're trees that will turn out to be way more low and bushy than a proper uniform binary tree. Another quick way of seeing the same thing would be, well, I would be guessing a uniform binary tree if it were true that for each binary tree of size, let's say n, I have the same number of ways of obtaining it by adding one leaf at a time at each step. But this is definitely not true, because if I have a very tall tree where, for example, at each step, the left child has a child, but the right child has no other children, so the spine tree, there's only one way of building that, because we have to add the cherries one at a time from the bottom to the top. Whereas if a tree is more balanced, there are plenty of ways of building it with this algorithm. So these are two ways to see that this idea of just picking a uniform random leaf will definitely not work. And because of both of these things that I just said, it should be intuitive at this point that the correct way to distribute the light among the leaves would charge taller leaves in higher generations, more than leaves that lie lower, because I need to obtain the correct average height, let's say, for my tree at step n. So hopefully I've convinced you that the question itself is non-trivial, but the answer is known since 2004. And in a very nice paper by Łuczak and Winkler, they answer this question positively. They show that there is a way to build these random trees in an increasing way, as I have asked. And in fact, they have a general proof for K-ary trees, which are the objects I described briefly before. Although, as we will see in a second, their proof is quite implicit in a way. It relies on, an induction argument and a max flow min cut kind of argument that shows that indeed a measure on the leaves, a probability measure on the leaves that creates a scheme building K-ary trees uniformly does exist, but it doesn't give an explicit one at all. Now, in fact, just to convince you a little bit further, the answer can be no, even for random tree models that are very natural and that potentially even converge to the continuum random tree, what I described before. And I had, there's a nice, small and very easy counterexample in a paper by Janssen from 2006. I was thinking I might be able to describe this counterexample for you, but I think I don't have that much time, so I'll just briefly skip it. And just say that for anyone who is familiar with Bien-Aimé Galton-Watson trees, the example is of a Bien-Aimé Galton-Watson tree actually with vertices having just 0, 1, or 2 children, and with a specific offspring distribution constructed in such a way that if you take this Bien-Aimé Galton-Watson tree conditioned on having n vertices, no such a growth scheme can be possible. And just to mention, people are still working on questions connected to this, even in this Bien-Aimé Galton-Watson setting that I just mentioned. There are some positive results. And William Fleurat just last year in a paper and in his PhD thesis gave a sufficient condition on the offspring distribution of this Galton-Watson tree for this growth scheme to actually be possible. And this is a quite natural log concavity condition on this distribution. Now, having said all of this, let me go back to the original setting of the binary tree and try to tell you a few more things about the actual measure on the leaves that would indeed grow a uniform binary tree of size n+1 from one of size n. And as we mentioned before, the uniform measure on the leaves is not it. let's try and see whether we can instead say something about the correct way to pick a random leaf to grow a uniform binary tree. And one really natural way of building this measure on the leaves would be to do this recursively and to just use the natural recursive structure of the binary trees. So the idea is I would like to compute the probability that given a tree of size n with an A-B split, by which I mean that the left subtree has size A and the right subtree has size B. In this case, I would say, so the original tree has size 3, 6, 7, 7 internal vertices. The left tree has size 2 and the right tree has size 4. So the split will be AB, and the original tree N will be A plus B plus 1. Okay, so I would like to choose my leaf by first deciding whether it will be a leaf of the left subtree or a leaf of the right subtree. Now, let's say that I will pick the left subtree with probability only depending on the size split on A and B. And let's call this probability C of AB. Now, I know some equations that my probabilities C of AB need to satisfy, because if I let P of A be the probability that a size A plus B plus 1 tree has an A-B split, so this probability is Catalan A, Catalan B over Catalan A plus B plus 1. That is the number of trees of size A times trees of size B, divided by the total number of trees of size n. Now, what must my probability CAB satisfy? It must satisfy that the probability of having, let's say, an AB split for a tree of size n plus 1 needs to be what? It needs to be the probability that a tree of size n had an A minus 1 B split, and then I choose to grow a leaf on the left, which indeed is one way to result into an A-B split, all right, plus the probability that my size n tree had a split of type A, B minus 1, and then I chose to grow the right tree. So this will happen with probability 1 minus C of A, B minus 1, where C of AB was the probability to grow on the left in an AB split. So this is the equation that I get for all A and B. And from this, I can actually recursively compute my CABs. So what we obtain, actually, just to give you a little bit of background about how this happened, this was in joint work with Alexandre Stauffer. We were working on quite different problems. We were interested in estimating some mixing times of certain Markov chains on trees and on triangulations. And we happened to need these probabilities and essentially to need the result of Łuczak and Winkler, but we were not aware of this result. And we were just in the setting of binary trees, which is much simpler than the general setting of k-array trees. And we just actually computed the explicit probabilities CAB and obtained this expression that is, in fact, I would say, quite nice, or at the very least, not bad. It was actually a guess in the sense that you can figure out this expression and then replace it into the equations it needs to satisfy and just show by induction that everything works out. And that the way to pick random leaf of your binary tree in order to grow a uniform binary tree would be to look at the initial split at the root, choose whether to grow on the left or right according to this probability that you compute as a function of A and B. And then once you've chosen to grow, let's say on the left, you have a new binary split with new numbers A prime and B prime for the split. And you compute C of A prime B prime in order to choose whether you're going to move left or right at that split. Now, it's I have little time, I believe, so let me well, okay, maybe let me just say really briefly something else on the discrete level, something we've later found with Nicolas and Robin, which I find quite nice and interesting, and what's somewhat frustrating, but still interesting, hopefully, is that we haven't been able to find a nice bijective explanation for this phenomenon that I'm about to describe to you. So I'd happily invite anyone to think about it themselves. But this weird expression for CAB, there is a sort of interpretation that you can give for it by saying that, okay, you're just going to choose left or right with a best of three game between the left tree and the right tree. You'll take the number of vertices in the left tree and the number of vertices in the right tree. And the first game will be won by left or right with probability proportional to their number of vertices. And so let's say the left one wins this time. So it has two internal vertices and three leaves. That's why it has probability 5 over a total of 14 to win. And the winning side will get an extra token. And you continue independently like this. The second game, the left tree will have probability 9 over 15 of winning, and the right tree will have probability, well, the opposite, whatever that is, of winning. Now, in this case, I've set right as 1, so right gets a new token, and the final game is played. And now you look at which side has won more games, and that is the side that you pick. So in this case, I pick the left subtree with probability C24. And if you compute the sum of the probabilities of winning 3 times and 2 times for the left subtree, you obtain exactly the expression CAB from before, which is quite surprising and which we weren't quite able to explain. So this is a completely explicit expression for the probability measure you have on the leaves of the binary tree, which is in fact unique if you ask for a very natural symmetry condition on it. This is the only solution. If you want to grow K-array trees, Łuczak and Winkler tell us that we can. We have no explicit expression for the probabilities involved in computing this, the values of this probability measure on the leaves in the case of K-array trees. And now I'll just give you a super brief view of a few results. Thanks to this explicit expression, you can actually find out a lot of things about this, which we call leaf growth measure on the leaves of Tn. And something quite natural would be, okay, if I let n go to infinity, in the same way as I did for my trees Tn with the uniform measure on the leaves, towards the CRT, that ended up giving me some sort of uniform measure on the CRT. Can I still do this in this case? And what are the large scale properties of these leaf growth measures nu n? Well, here in this picture, I'm showing you the measure on the leaves by drawing them in a color closer to red if they have larger measure. But this is not that showing you things that clearly. Things become a bit more clear if I draw the leaves with circles of area proportional to their actual leaf growth measure. And the root of this tree is the black dot you have on the right. Notice that it's quite true that the leaves that are further away from the root tend to have bigger mass for this leaf growth measure. But we can say way, way more about this. And in fact, something that's interesting is that whereas the typical measure of a uniform random leaf is of order 1 over n to the minus 1, this leaf growth measure is concentrated on a quite small set of the leaves, and the typical order of the measure of a random leaf chosen according to this leaf growth measure is actually of order n to the minus gamma for a certain gamma that we're actually able to compute explicitly, and which is quite far from 1. It's something like 0.8. Is this 3 times 2 minus square root 3. And in fact, again, super briefly, what happens is a sort of multifractal phenomenon. So actually, the typical measure of a random leaf is not really what governs the various moments of the measure of a random leaf, which we can compute. We can compute the expected value of nu n of ln, where ln is a random leaf chosen according to nu n. And that's of order n to the minus a certain amount, what you see there, which is not gamma, as you notice. And that picture with lots of spike, in order to give you an idea of what's really happening, is if you turn around the contour of your tree and record what the nu n of the leaf you see actually is, you see this kind of completely spiky, fractal, and quite complex sort of picture. So this is what is going on. We're able to give a characterization of the exponents for all of the moments of this nu n of ln random variable. We are able to do what I said we might want to do, so actually pass to the limit and describe a measure on the leaves of the Brownian CRT, that is the limit of these discrete leaf growth measures. This is a measure that is singular with respect to the uniform measure on the CRT. And something else, for example, that we're able to do is actually compute the explicit distribution of the height of a random leaf growth leaf instead of a random uniform leaf, which one can compare. And finally, just to say where one might want to be going next, well, this is a very brief note. Actually, now we've built these trees Tn in a joint way on the same probability space. So you might wonder whether the CRT is actually an almost sure limit of this sequence of random trees. And the answer is no, which we can prove. But the fact that the answer is no is actually, in a way, a sign that this growth dynamic is actually quite interesting. And something that one might want to work on is consider actual limiting dynamics that happen on real trees. So in a sense, an actual Markov process on real trees that for which the law of the Brownian CRT is stationary. This has actually been introduced in a paper that's gonna come out soon by Adriano Stwicht and William Fleurat and Nicolas Curien, who talk about these limiting dynamics in the continuum by directly defining them in the continuum setting. And some questions would involve the type of convergence that one might show from the discrete dynamics that I've described to you to this sort of continuum dynamics. But I think I've taken way too much time, so I'm happy to stop here and take any questions that there might be.
Thank you, Dr. Caraceni, for this nice talk. Are there some questions, please? I have a general question, but I think you have already given the answer. How do you explain that the height of a random binary search tree is of order log n, while the height of a full binary tree is of order square root of n? There is a big difference between the two heights.
Indeed. Yes. So of course, you can just compute this. So on one side, something that I have not mentioned, and which is worth mentioning, especially for anyone who hadn't seen the Brownian CRT before, is why is it called Brownian, right? So there's some kind of Brownian motion involved. And one way to understand quickly why many models of trees have height of typical order square root n is that there's a natural bijection with Dick paths, so sequences of plus and minus ones with that are essentially walks, discrete walks that always stay positive, start at 0 and end at 0 at a certain time 2n. And the height of a tree essentially corresponds to the maximum of such an object. And if you sample such an object, you wouldn't be surprised, even though it is essentially a random walk, but with some conditioning, both of coming back to 0 at a certain time and on staying above 0 for all the time in between, the order of magnitude for the maximum will be square root n, as you would expect essentially for a random walk that's happening up to time n. So this is a quick heuristic to explain why these trees have size square root n. As for the log n size of the recursive type of trees, I tried to give an explanation that was a bit quick and not quite precise, but I think it should give an idea that that's indeed the case. Just the fact that if you build your tree by taking n steps of this operation that just adds a pair of leaves, at each of these steps, either your height increases by 1 or it doesn't increase. Now, at the kth step, by how much does the height probably increase on average? Well, it increases by 1 with a probability, that's the probability of picking a leaf that was at height exactly maximum height in the previous tree. But now you expect those to be few. If that is true, if you had only one top leaf, for example, at every step, then you would increase the expected value of the height by 1 over number of leaves.
You must have at minimum 2 leaves in the
Actually,
top.
at minimum 2, that's correct.
Yeah.
So let's say 2,
Okay.
but even 8, I don't know.
Okay. Okay.
If that were the case, you'd be increasing by 1/k, where k is the number of steps you've taken so far times the constant. And so if that is the case, then you'd get a constant maybe times a harmonic sum, and you'd get log n after n steps. So this is it's not quite a proof, but in fact it can be made into an actual proof.
Okay, thank you. Another question about the nice probability CEB. To prove this, to obtain this probability, you have proved at first that the CEB satisfies some recursive equation, and after you use some bivariate homogeneous function to some bivariate generating function to obtain the coefficient CEB.
Yes.
Okay.
So,
okay.
Wait. Yeah, just to. Yeah, it's I mean, from this equation and from the values that are obvious for a b equals 0 or whatever your starting point is, and if you want to enforce it, you'll probably want a symmetry in CAB being 1 minus BBA. Then you can compute everything.
Okay.
And this finding this expression was just really, we tried to figure out what function it could be, and this was a candidate, and it satisfies all the equations, and it's the only thing that can. So yeah.
Okay.
So it's not very insightful as a proof. That's why I showed you this possible alternative interpretation that I think would be very nice to actually prove directly somehow by some sort of bijective argument or more combinatorial actual approach, rather than just saying, okay, I know you get this result.
I think in this case, the bivariate generating function can be a useful tool to obtain the expression of CEB.
Yeah.
Are there other questions, please? Okay, about the uniform probability mu n measure on VTN.
Yeah.
Is it exactly mu n of some random tree for some given tree is exactly 1 over the Catalan number? Because it is the uniform to pick some tree of size n.
Okay, so in the notation that I'm using, I never gave a name to the law of what I call Tn, that is 1 over the Catalan number. Okay. What I called mu n was an extra object that was defined on the vertex set of the tree, and it was the uniform measure on the vertices. So I was giving each vertex probability 1 over, let's say, 2n plus 1, if we're not counting the root and if we're having size n.
Okay.
So it was just in order to get this uniform measure then on the limiting Brownian tree.
Okay. Some other questions, please?
I think there was someone maybe wanting to ask a question.
Yes, I think so. Other questions?
Here for a second.
Okay, I have a general question.
Okay,
and
sure.
Intuitive question. If we know the position of the leaves, the position I mean by position, the generation who it is the are the leaves. we can know exactly the tree. We can construct exactly the tree. For example, the tree has two leaves at generation 1, 4 leaves at generation 2, 6 leaves at generation 3, and so on, for example. Canals obtain almost surely the tree, exactly the tree.
Well, I would. Okay, so there's at least one problem, but I don't think that's the relevant part of the question, is if you know just the number of the leaves, you wouldn't know.
Not only the node, but the position, the generation, the levels where are the leaves.
Yes, yes. But okay, so if I look at all binary trees that have, let's say, one leaf at level 1 and 2 leaves at level 2, there are 2 trees doing this because, oh, so, sorry,
No.
it seems like my gestures triggered some.
It is nice.
Yeah. Because okay, so the left child of the root could be the one that's parent to the generation 2 leaves, or it could be the right child of the root.
Yes, sure.
But I think there are probably even worse problems than that. I don't think it's only a matter of direction.
Okay, other questions, please? If not, we have to thank again Dr. Caraceni for this nice talk. And see you next week, 7 October, for another talk about the polio ears. Thank you.